Hey there. So today I'll be talking about the Heisenberg uncertainty principle, which has to be one of the most misunderstood topics in all of quantum mechanics. Alright, so we know that the electron exhibits both particle-like behavior and the wave-like behavior, the double slit experiment and the photoelectric effect. The Heisenberg uncertainty principle states that there is a limit to how well we can measure where the particle is going and where the particle actually is. Its velocity and its position, the knowledge is limited. Now, a famous physicist called De Broglie came up with this equation which states that the momentum is inversely proportional to the wavelength. So from now on we'll talk about the wavelength instead of the momentum, because knowing one will allow us to find the other. Now this is a wave. This is a water wave, and here is it. So where is its position? So we can only localize it to one position, which is this. So we have localized it to a wave packet where it has most probability of turning up. Now what is the probability of a ball turning up here? So in order to quantize its wave-like behavior, the wavelength, it will have to be very small and inside this ball, because there will be a huge spike in probability where the ball actually exists. Okay, in order to be sure of where the particle actually is, we need to combine more and more wave functions in order to generate a smaller wave packet. So this wave packet is small, so we have reduced the uncertainty in our position, but now we had to increase the uncertainty in our wavelength, because we cannot measure the wavelength of just a pulse very accurately. Similarly, in order to increase the uncertainty in our wavelength, we have to combine broader and fewer waves, and that's how we will increase the uncertainty in the wavelength. But here we had to decrease the uncertainty in position because the wave packet is now more spread out. This is the mathematical statement of the Heisenberg uncertainty principle. This is actually a very small number, and which is why we don't notice quantum mechanical effects on a everyday scale. For example, if you find me here, I will almost certainly be here and not spread out in a way like this. So a few misconceptions. Particles don't have a fixed momentum or position, and it's not because of the difficulty that we are unable to find it. It is actually because of the wave particle duality behavior that they exhibit, that we cannot figure out the position and the momentum precisely. Although we do gain values after measurement, these are allocated randomly along the wave the wave function of the particle, which is the probability density function of what values a certain property can take. Another misconception is that it is because of the lack of our knowledge. It is not true. With all the knowledge quantum mechanics says it is possible to have, we still wouldn't be able to violate the Heisenberg uncertainty principle.